Hey there, and welcome to the Science Hutch, my fellow physicists. We're doing free body diagrams. This is video number 2. In the first video, we just listed out 5 forces to look for on and to draw on free body diagrams. Now we're just going to start practicing them and drawing some forces all over the place here. So I'm going to get this, I feel like orange today. We're going to, first of all, the fast and easy one is to look for the weight, which we're labeling capital F for force, lowercase g is a subscript for force of gravity. And really, it doesn't matter what the object is doing. You're going to see, if it's on the planet, usually planet Earth in our case, then you're going to see a force of gravity on it. And I'm just assuming that this is the same rock. It's having a very busy day. It is got the same force of gravity on it. So I'm drawing these forces of gravity about the same length to show the same magnitude. Or I like to say that the length of the vector shows the strength of the vector. And so we're looking at the same strength in all these forces. All right, next we're going to look for normal forces. Normal forces mean contact. So here we have a normal force. This rock is in contact with this ramp, and it might be helpful to you to picture a new x and y axes that are tilted to fit the ramp. And so there we go. We could also say, instead of x and y, we could say parallel. This symbol means parallel. This symbol means perpendicular. So you could have parallel to the ramp and perpendicular to the ramp axes. And the normal force is always perpendicular. Normal means perpendicular to. This one's really easy down here, number 6. Normal force. And by the way, I'm using a handout that I stole from the physics teachers. Good resource set for physics teachers and for physicists to practice. Normal force down here as well at the bottom left, where we're going to see we're tilting our axes again, and so we have a perpendicular and parallel axes, and we have more down here at the bottom. Dash lines so they don't look like I'm drawing more force vectors. And then just once you've got those, it's really easy to draw your normal force right along that perpendicular axis. Oh yeah. Now down here in the middle, we've got a block here, and the rock is resting against the block. So we're actually going to need to draw another normal force that is perpendicular to that block. The block is pushing the rock up the ramp. Now, since we have two normal forces, I'm going to label one normal force 1 and the other one normal force 2. What else do we have in our checklist of stuff? We went through weight, we went through normal force. Let's look at friction forces. So yeah, stick with drawing orange vectors here. Friction forces. So in here, friction prevents sliding. This is called static friction. And we're going to draw this pointed against the way that the sorry, that the rock would want to slide. And so static friction, and so we're using a little s there, and I mentioned that in the last video. No friction in number 6, because friction is a lazy force. It only exists when it has to. And then down here the rock is sliding, but it's frictionless, so we have no friction there. And in number 8, the rock is being held by the normal force on the ramp, so friction doesn't need to exist and therefore does not. And in number 7, we have a string there, so we're going to see a tension holding it up. Friction is not needed there as well. Speaking of tension, let's look for some tensions. So tension force is the 4th force on our list. Here we go. Here's some tensions. This one needs to be drawn equal and opposite to the weight in order to hold the weight up. So it should be the same length to show the same strength. Here in number 4, we see two equal and opposite, not equal and opposite. We see two equal amounts of tension because the ropes are at equal angles. And then if you know about components, the vertical components of these forces should add together to equal the weight vector that's pointed down. So if you draw these head to tail with each other, then they should actually add up to equal the weight. I've drawn them a little bit too long there, but ideally they would be the same length as the weight. As you can see, that's grossly inaccurate there. Maybe I'll fix this here just to fix it for our type A personality friends out there. And there we go. All right, so that would be a little bit more accurate. And then you don't draw components on a free body diagram, so we want to get rid of those. And then you also imagine little left and right components here that are made by these tension vectors at angles, and the left and right should cancel with each other to keep everything from swinging left and right. Now, over here in number 5, we're going to see, let's see, here we go, orange. We're going to see that this more vertical string has more force of tension in it than this more horizontal string. And the reason why is because what are they holding up? They're holding up against a vertical weight here. So the one that's more vertical is more in position to respond to that vertical weight and to counteract it. And so really the force of tension 2 is pulling more to just hold the rock from swinging against the left pole of force of tension 1. And it is contributing a little bit, a little vertical vector there, but the force of tension 1 is contributing more. So when you add those together, they cancel out with the vertical force of the weight. So there's that. Number 6 is done. Number 7, we have another string here, and this force of tension is balancing out with a component of the weight. If you imagine that the weight is acting on these special axes we've drawn, here are the parallel component, force of gravity parallel, and the force of gravity perpendicular to the ramp. So the force of gravity feels like it's pulling double duty here. It feels like it is making the rock not float up off of the ramp, so it's holding it against the ramp with this perpendicular component, but then it's also making the rock feel like it wants to slide down the ramp with the parallel component there. And so we need two forces to balance out the one force of gravity in this case. Tension is balancing out with the parallel component, and the normal force is balancing out with the perpendicular component. Now again, when you're drawing free body diagrams, you don't include components in your final product there, so I'm going to erase them. Number 8 is all done, and number 9 is all done. So thank you for tuning in. We're going to level up and look at some harder examples here in our next video. So this was the science. I was a science Hutch, and you're the physicist. Keep on physicsing.